Hello everyone. Today we're going to look at force and motion. At the end of this chapter, you should be able to understand Newton's first law of motion, know different types of forces, know and be able to apply Newton's second law, and you should be able to understand the idea of equilibrium. Okay, let's start. So, the first section of this chapter, we're going to look at Newton's law of motion. So, imagine a box lying on a table. If you want the box to move, you need to push or pull it. You need to act on it with a force. If you do not apply a force, the box will remain at rest. Once the box is moving, a force is required to change its velocity. For example, a friction force might cause it to slow down, or you might continue to push it to make it accelerate. If there is no force at all, the box will continue to move at a constant speed. This might be difficult to imagine. Objects around us are constantly subject to force like gravity and friction. But it may help to think about, for example, a stone sliding across ice. It takes a very long time to slow down because the forces acting on it are very small. Any change in velocity of an object is caused by a force. This is one of the most important principles of mechanics. So, here is Newton's first law, which states an object continues to move with constant velocity or remains at rest unless acted upon by an external force. So you need to notice here that this law refers to the velocity rather than just the speed of the object. So a force is required to change the direction of motion as well as the speed. Once you apply the force, the box will start to accelerate. If you want to produce a greater acceleration, you need to push or pull harder. But you also know from experience that heavier objects are more difficult to move. So the force required to produce a given acceleration depends on the mass of the object. It is in fact directly proportional to it. So we just talk about Newton's first law. So Newton's first law states that if an object is seen to speed up, accelerate, or slow down, decelerate, there must be some agent causing the change, which is the force. And Newton named it Newton, and we always use capital N to represent the force. And 1 Newton equals to 1 kilogram meter square per second. And that's a unit for force. So there's other forces exist. So we talked about friction. So imagine a car is moving forward, so there might be a driving force. Or if someone is pulling the car forward, then there may be a tension. We'll look at different types of forces later on in this chapter. Right. Okay, so here comes Newton's second law. As we just talked about, that force is directly proportional to the mass of the object. So here comes Newton's second law. It says when a force of F newtons acts on an object of mass m kilogram, the acceleration a meter per second squared is given by F equals to ma. And this is Newton's second law. Right, let's have a look at an example. Okay, so in this example, it says a car of mass 1,200 kilogram is pushed with a force of 150 Newton. So in this case, we assume that there is no other forces acting on the car except the force of 150 Newton. Calculate the acceleration of the car and find how long it will take to reach a speed of 1.5 meters per second from rest. Okay, so let's do the first part to find out the acceleration of the car. So from Newton's second law, we know that F equals to ma. So let's write the formula down first. My pen is not working. Just bear with me a minute. Here we go. Okay, it's not the best handwriting, but hopefully you can understand. Okay, so what is the force? The force is 150 Newton. And what is the mass of the car? That's 1,200 kilogram. So that means 150 equals to 1,200 times by acceleration A. So to work out the acceleration, we just need to use 150 divided by 1,200. And the acceleration A will come out to be 0.125 meter per second squared. Okay, so let's move on to the next bit, which will ask us to find out how long will it take for the speed to reach to 1.5 meters per second front rest. Right, so that linked with the previous chapter we've done. So we have to use the Suva equation. Okay, so let's write down the SUVAT. SUVAT. Okay, so S stands for the displacement. We don't know anything about that, so let's cross it out. Do we know the initial speed for U? Yes. And the question says start from the rest, so the initial speed is 0. Do we know the final velocity? Yes, it's 1.5 meters per second. Do we know the acceleration? Yes, we just worked it out. It's 0.125. And we're looking for the time. So let's put question mark next to time. Okay, so let's have a look at your Suva formula and find a formula which does not involve S. Okay, so hopefully you can find out that the formula we're going to use is V equals to U plus AT. So this is the formula we need to use. Okay, so let's substitute the values in. So V is 1.5, U is 0, A is 0.125, and then times by T. So that means T will equals to 1.5 divided by 0.125. And that will come out to be 12 seconds. You can work it out in your calculator. Okay? All right. So here's the answer for example 1. Great. Let's move on to the next example. Okay. Example 2. So here it says, a box of mass 3.5 kilogram is being acted on by a single force F equals to 14 negative 21 newtons. Find part A, the vector acceleration of the box, and part B, the magnitude of the acceleration. All right, so we talked about before that force and the acceleration could both be vectors, so have directions. Hence, in this case, the force is written in the column vector form. Right, let's start with part A. Right, so let's write down Newton's second law, the formula F equals to ma. And since we're talking about, we're using vectors, so let's underline the force and underline the acceleration to represent their vectors. Okay, so let's substitute the information we know. So we do know that the force is 14 minus 21, and that equals to the mass, which given to us is 3.5, and then times by the acceleration. So to work out the acceleration, we just need to divide 14 by 3.5 and divide it by negative 21 by 3.5. So we will get that acceleration A equals to 4 and minus 6 meter per second squared. And I should underline them because acceleration is actually a vector in this case. Okay, right, part B, find the magnitude of the acceleration. So to find the magnitude of acceleration, that equals to the square root of the component squared. So that'll be 4 squared plus, I think, minus 6 squared. Okay, so that would be 16 plus 56, which will come out to be square root of 52. Or if you put in a calculator, that will be 7.21 meter per second squared to 3 significant figure. Okay, excellent. Let's look at the next example. Okay, right, so example 3. So in this example, it says a block of mass 1.2 kilogram slides across the floor with the initial speed of 3.6 meters per second. It slows down due to a constant friction force of magnitude 9 Newton. How far does the block travel before coming to rest? Okay, so again, we're going to write down the meter per second law F equals ma to start. Okay, and let's substitute all the information we know. So here we've been given that the block weight is the mass of the block, not the weight, sorry. The mass of the block is 1.2 kilogram, okay? And initial speed, we'll use that later. And here it says the frictional force is 9, and that is the only force we know, so let's use that for that. So we have 9 equals to 1.2 A. Okay, now let's just pause and think about it again. Is this correct? Well, if the block is moving across a surface, which direction would be the frictional force acting? Well, let's just draw a diagram and think about it. So, if this is my block, this is the surface. Okay, right. If we're going in this direction towards the right, okay, so we're traveling towards the right-hand side, and let's say this is my positive direction. Which direction would the friction force be? Well, the friction force will try to slow down the block. That means the friction force actually should be acting in the opposite direction. So this is our friction force. So if I'm assuming that the block is traveling towards the right and the friction force is actually acting towards the left-hand side, so when I substitute the number into the formula, so this 9 Newton, we have to change the sign because it's in the opposite direction. So let's give it a negative sign in front of n, the 9. Okay, now we can work out A. Now, the block is moving forward, so that means it's accelerating towards the right-hand side. Okay, right, so let's put in the calculator. So to work out A would be equal to minus 9 divided by 1.2, and A come out to be minus 7.5 meter per second squared. So when the acceleration is negative, what that means is that the block is actually slowing down. Okay, right, so let's move on. So in the question, actually asks work out how far does the block travel before coming to rest. So we need to use Suva equation again. So let's write down our S, U, V, A, T. So we're looking for how far it travels. So S is the unknown. Do we know the initial speed or initial velocity? Yes, it starts with initial speed of 3.6 meters per second. Do we know its final velocity? Yes, and the question says it's coming to rest. So the final velocity V is 0. And we have just worked out our acceleration is minus 7.5. And we don't know time, and we don't need to use it. Let's cross it out. So we're looking for a pseudo equation which involves SUVA but not T. So let's have a look at your formula book and find out which formula you could use. Okay, so I think the formula we're going to use is going to be this formula. V squared equals to U squared plus 2AS. Let's substitute the formula, the information to the formula. So V squared. So V is 0, so we have 0 squared equals U squared. So 3.6 squared plus 2 times by minus 7.5 and then times by S, which is our unknown. Okay, so then we can put in a calculator and work out what is 3.6 squared. So that would be, so 0 equals to 12.96. And 2 times by minus 7.5 will give you minus 15 and S. So rearrange formula, we can work out that 15S equals to 12.96. And that means S will equals to 12.96 divided by 15, which come out to be 0.86. Oops, sorry, can't really read that. 0.864 meter to 3 significant figures. That's our final answer. Okay, right, great. So hopefully you have now understand how we could use the Newton's second law, F equals ma, and hopefully you have an idea of what is Newton's laws. So what I like to do is to have a look the exercise from the book. So exercise 21A. And I would like you to try a selection of questions from this exercise, please. So if you don't have the book, feel free to pause the video and you can have a look at the questions on the screen. And here are the answers for exercise 21. Please check your answers after you've done the work. And we should now move on to the next section.